I was told over lunch that one of the things that Alonzo Church used to do when he began his lectures was he would spend the first 5 minutes patiently and thoroughly cleaning the board. And I suppose he was collecting his thoughts while he was doing that. And that's probably a good idea. Maybe I should have followed his lead rather than enlisting help here and jumping right in, but I'm going to pursue a different course here. Okay, category theory. What is category theory and why do I need to know something about it? Not I, but you. Category theory is, as a first approximation, it's the abstract algebra of functions. Okay, let that sink in a little bit. It's the abstract algebra of functions. And of course, one of the themes of this meeting, and of course one of the themes of theoretical computer science, is that the lambda calculus is a calculus, a formal calculus for manipulating functions, for specifying, manipulating, and calculating with functions. So it's not surprising that there should be some kind of connection there, right, between category theory and lambda calculus. And of course, there is, in fact, a very deep connection. We're looking at the same thing, essentially, from two different points of view. Once from a kind of logical point of view on the lambda calculus side, and once from a more mathematical, if you will, or algebraic point of view coming from the category theory side. And really, these are just two different ways of looking at the same structure, the same idea, and they're complementary. And that's what's so fascinating about this connection is you can look at this same thing in these two different ways, the algebraic way or category theoretic way, which actually has a kind of geometric character, which you'll see as we get going, or the logical syntactical way. And those two different points of view are complementary, and they feed off from each other, and they suggest some interesting results. So that's the kind of background there, motivation for learning and using category theory in this setting that's so far removed from the original source of category theory in algebraic topology and homotopy groups and homology groups and all that stuff. So it's amazing that category theory has filtered through the rest of mathematics, even into theoretical computer science, and now it's really a kind of foundational discipline with these deep connections to logic. Okay, so let's look at the algebra of functions. What do I mean by functions? Well, let's just start out. So what I really mean is abstract functions. I mean any kind of process or assignment or procedure or expressions which can be read in a functional way. So it's the abstract algebra of abstract functions, if you like. But let's start out just by thinking of familiar set theoretic functions on sets in order to arrive at the basic principles of category theory. So we'll look at functions. We'll look at functions on sets. So suppose our sets, I'll write them with capital letters here. These are just some sets, right? And then a function, f, I'll write like this, going from A to B. So that's just to remind you that's a subset of the Cartesian product of A and B, which is therefore a relation on A cross B, right? So f, so here, officially, so in set theory, if you want to be formal about it, in set theory, what is a function from A to B? Well, it's really a subset of pairs, right, such that, and then we have the usual condition, right, for all A and A, there's a unique B in B such that the pair A, B is an element of that relation F. So that's the official definition of a function, but we're not going to really use that. I'm just going to think of functions in the kind of intuitive way of taking an element of this set and returning an element of this set. Good? How do functions behave? What operations are there on functions? Well, the basic operation that we're interested in category theory is this. If I have a function f from A to B, and I have another function g from B to C, then there's this operation of composition, g, which I write g after f. And the way that g after f works is, of course, g after f applies to an argument x from A to give me g applied to f applied to x. So that's the basic composition operation that we're interested in. And then there's another operation which is even simpler, and that is the identity function. That is, for each set A, there's an identity function, which I'll write like this, 1 sub A on A, and 1 sub A for any element x is just x. It's the usual identity function. So that's the basic data. We have a composition operation, and we have the identity function operation. And then we have some laws, and the laws look like this. If I take a situation like this, I have F, G, H, and first I compose like this, G after F, and then I compose the whole thing with H, so that's H after G after F. Or first I do this, that's H after G, and then I compose this whole thing, and that's H after G after F. Then the result, H after G after F, is equal, regardless of which way I do the composition. Because if you just unwind this formula, you see that both of those things are equal to H of G of F of X, right, for every X. So these things are equal. That's the associative law for the composition operation. And then the other law is if I take A, and I take any F like this, and I take here the identity on A, well, then this composite, F after the identity on A, is equal to F. And similarly, if I take here the identity on B, and I compose, then this composite, 1B after F, is also equal to F. Right? Because this function doesn't do anything. Right? So I take the x to x, and then I apply F. That's the same as just applying F. And similarly, this function doesn't do anything. So those are the basic laws, and that's really all the structure of sets that we want to use or make use of in our definition of a category. The idea is now we abstract away from all the rest of the things that you know about sets, subsets and Cartesian products and elements of elements and power sets. We forget about all that junk, and we just look at these algebraic operations. So how do you go about abstracting away from a mathematical point of view? Well, you give an axiomatic description of the structure you're interested in, which captures this much of the situation, but then you look at anything that satisfies that axiomatic. And that's how you abstract away from the specifics of this particular example. So the general definition of a category is an abstraction from this example. So the definition of a category is this. Well, first of all, it consists of two kinds of things, and they're different. It's a two-sorted theory, technically speaking. There are the objects of the category, which are playing the role of the sets in this example, and there are what we'll call the arrows of the category, which are playing the role of the functions in this example. So I'm going to just keep with that same notation. So I'm going to write the objects with uppercase and in general, and I'll write the arrows with lowercase. And in addition, there's some more data in the definition of a category, namely, so for each arrow F, there are given objects called the domain and the codomain of F. So this was kind of implicit in this, but if I have a function, then it goes from some specified set to some other specified set. So we're going to put those in as explicit operations, and the notation will be this. So the domain of F is on the left of the arrow, the codomain is on the right. And we write F goes from the domain to the codomain. And then for each object, A, there's an assigned an arrow. So here's the identity arrow, 1 of A. And it, of course, goes from A to A. That's its domain, and that's its codomain. And then the axioms. So this is the data, and then we have the axioms, if you like, or the laws Well, those are just these laws that I just wrote down right here. Associativity and unit. Unit. So the axioms are just those two laws. It's H after G after F is H after G. After F, whenever those composites make sense. Composition is only defined when things line up, yeah? Oh, sorry, I forgot to put in the composition. Let me put that in. Oops. There's one more operation, composition. For each composable pair, that is, arrows like this, where the codomain of this one is the domain of this one, we have a composition operation, G after F, going from A to C. So that's one more bit of data, is this composition. So identity, composition, domain, and codomain. And then I have, as I said before, the laws. The laws are associativity. So that was H after G after F is H after G after F, and the unit law. So that's 1 B after F equals F after 1 A. Okay, so that's the definition of a category. It captures this example as we just checked. Yep. Yeah, okay. Yep, sure. Thanks, yeah. As we just checked, it captures this example. We just looked and saw that this example satisfies these conditions. So our first example of a category is the category which I'll call sets, that has the objects are sets and the arrows are functions. Let's have some more examples of categories, because there are lots and lots of examples. This was just kind of a place to start. Well, there are some interesting finite categories, just to give you a different flavor here of what's going on. For example, there's the category 1, which has one object, which I won't even bother to give a name, and it has one arrow, namely the one it has to have, its identity arrow. So that's what it looks like there. Now you're thinking, well, what is that object? I'm saying, just take something and call it an object of this category. Put in formally any other thing, call it the arrow of the category, right? Define the domain and codomain in the obvious way there, and that's it. You don't have to compose anything. I mean, this is composable with itself, but of course, all the composites are equal to itself by the unit law, so we're done. There's a category 2. It has two objects. I'll give them different names, like that, and it has one arrow between them. Now I should put in these identity arrows, but they don't really do anything, and there's no other composition around. So that's it. That's the category 2. And similarly, there's a category 3. Now you can kind of guess how this is going to go on, right? It has these arrows. It has these identity arrows, which I won't draw after this example. And then there is a composite that you can make. Let me put that in. And then nothing else. There are no more composites to be made, and we're done. So that's the category 3. That looks like a B, doesn't it? 3. There's another category 0, the empty category. It looks like this. It has no arrows and no objects. Okay? And so now you get the idea, right? You can make any kind of crazy. You can make lots of finite categories. You just say, take some objects, let's call them A, B, C, D. Put in some arrows, but make sure that any time you've made a composable sequence, you have to say what the composite is going to be in order to specify your category. And you can make finite categories like that very easily. So there are lots of finite categories involving some finite family of objects and some finite collection of arrows, and then you define your compositions and identity operations. So that should give you a sense of how many different kinds and simple kinds of categories there are. Let's look at some other more natural kinds of categories. So for example, there's a notion of a poset, partially ordered set. Everybody know what a poset is? partially ordered set. Everybody knows, almost everybody knows what a partially ordered set is. So let's suppose I have a poset P. It has a partial order on it. That's a reflexive, transitive, and antisymmetric relation on the set P. And I'm going to make it into a category. Poset category. Like this, I'll say, given some elements P and Q, I'll say there's an arrow from P to Q just in case P and Q stand in this relation, PQ. So because of the way I've defined this, there's at most one arrow between any two objects. So I put formally in an arrow just in case these things stand in that relation. Why is this a category? Well, the identity arrow is in there because of the reflexivity of the relation. The composition is in there because of transitivity of the relation. You don't have to wonder what is the composite. It's there because there is at most one arrow between any two things, and there is one by transitivity. Okay? And what about the laws? Here's a little check. What about the unit and associativity laws? How do I know that they hold? Keep trying. Yeah, there's at most one arrow between any two objects. So the laws are equations among arrows, right? If I have here P, Q, R, associativity, for example, looks like this. And now it says P, Q, R, S. And associativity says, take this arrow, compose it with that, and compare it with this arrow composed with that. And it says these are supposed to be equal. But any two arrows between given objects are equal in a partially ordered set. And so the associativity law holds for free. And similarly, the unit law will hold for free. Okay? So a poset is a category in this kind of trivial or degenerate way, if you like. It's a category with few arrows. Few arrows. By which I mean at most one between any two things, P, Q. A kind of complementary phenomenon is a category with very few objects and lots of arrows. This one has lots of objects, perhaps, and very few arrows. Let's take a monoid, M, with a multiplication operation and a unit element as a category. Who knows what a monoid is? Oh, great. Okay, almost everybody. It's like a group without inverses, right? If you know what a group is. Groups have inverses, like the additive group of the integers, right? Has the negative numbers. If you just take the positive numbers, 0, 1, 2, and so on, the natural numbers, that's a monoid under addition with the 0. So a monoid can be regarded as a category. Objects, well, there aren't really any objects in there. Namely, we just put in a formal object. So we'll go like that. A formal object. And then we regard the elements of the monoid as arrows on that formal object. So for every element of the monoid, we put in an arrow. And now, because this arrow has the same domain and codomain, right, any two things are composable. Yeah? And so if I have M here and I have some N here also coming from the monoid, well then I have to make a composite. What should it be? I'll just take the group multiplication or the monoid multiplication there, and that will be my formal composite of these two elements. And finally, I'll take the unit of the monoid and make that my identity arrow. Good? So now I have identity, I have composition, I have arrows and objects, domain and codomain are obvious, and now I have to check the laws. So what about the category laws now? What about the unit law? Well, that comes from the unit law of the monoid, right? The U acts as a unit for the product, but the product is composition. What about the associativity law for composition? Well, that comes from associativity for the product in the monoid. It's part of the definition of a monoid is that the product is associative. So I get those for free, basically, by the fact that I've assumed I've got a monoid. So a monoid is then a category, but it's a special one. It's a category with just one object. And in fact, it's exactly a category with just one object, right? You can interchange those two concepts. They're the same thing. A category with one object only is exactly the same thing as a monoid. Good? Say again? Right. So that's a trivial monoid. That's a trivial monoid that just has a unit element. It's a trivial monoid. It's the same category. Okay? Right. The notion of maybe the first structural notion in category theory, or notion that can be defined entirely in terms of the language of categories, but a very useful and important mathematical notion, is the concept of isomorphism, right? You've encountered isomorphism in lots of different ways. Sometimes people say things are isomorphic if they have all the same properties. It's not really right. I mean, it's true, but it's not the definition of isomorphism. The definition of isomorphism is a category theoretic one. So in any category, objects, so let's do it this way. An isomorphism from A to B, let's say F here, is the following. It's a map A, it's a map F from A to B together with, or depending on how you want to do things, such that there exists a map G coming back such that G after F is the identity on A, right? That makes sense. G after F is the identity on A, and F after G is the identity on B. F is the identity on A. F after G is the identity on B. Look, it only uses the concepts of category theory, composition, identity. So now, if you give me a category, I can tell you what the isomorphisms are in that category, right? For every category, there's a canonically determined notion of isomorphism in the category. So if you look at, well, we don't have enough examples here yet to see what isomorphisms are. In sets, isomorphisms are bijections of sets. In a poset, well, isomorphisms will be what? It will be P and Q such that P is less than Q and Q is less than P. So it'll be identity in a poset. Isomorphism is identity. What about in a monoid? What is an isomorphism in a monoid? Yeah, it's an element of the monoid that has an inverse. So monoid M, suppose we have some little m in here, which is an iso in the monoid. That means there's some element, let me call it M inverse, such that this is the unit and this is the unit. So an element, an invertible element, an element with an inverse. And in fact, it's easy to show that inverses are always unique when they exist. So maybe you're familiar with the definition of a group. So a group is a monoid, so a category with just one object, monoid in which every element, every M in M has an inverse. So a group is a category with one object in which every arrow is an isomorphism. It's the same thing as the usual definition of a group that you've seen using equations and operations. Okay? Okay, yeah, that's the second time I've been asked. Just keep asking and hopefully it will happen. Yep.
What? Don't keep asking now.
Remind me from time to time. Okay. Okay. So those are some examples. But that's only one kind of example. They're kind of degenerate in a sense, right? Because these had lots of objects but only a few arrows. This has just one object and possibly lots of arrows. Let's look at some more kind of general examples. And now, in fact, we have the material to build some examples, even if you're not familiar with them. We can make the category of all posets. So what is an object is a poset. Objects are posets, partially ordered sets. Right. And the arrows, well, these will be functions that preserve the ordering, or take the ordering here to the ordering over here. So those are usually called monotone maps. Monotone maps. So that is, if P is less than or equal to P prime, then F of P over in Q is less than or equal to F of P prime, where this is the ordering on P, and this is the ordering on Q. So that's the notion of a monotone map. And that makes a category because basically we're taking certain functions, right? And then we define the associativity, we define the composition to be composition of functions. We define the identity to be identity of functions. You have to check that the composition of monotone maps is again monotone and that the identity map is monotone. But once you do, you get the laws for free from the laws for sets. So that's an example there. What about the category of monoids? Yeah? A lot. Okay, good. Really? Okay, wow. Maybe I should write with 2 magic markers. It's blackboard bold. Yeah? Okay. So there's the category of monoids. So the objects, is that better? Objects are monoids, M, N, etc. And the arrows are homomorphisms of monoids. They look like this: F, M, arrow, N. They look like they're homomorphisms. I have to squeeze this in the corner, so it's going to, this one is an exception. It's going to be a little smaller. Homomorphisms of monoids. What's a monoid homomorphism? Well, it says F of M times N equals F of M times F of N, and F of the unit is the unit, right? It's a usual notion of an algebraic homomorphism of algebraic structures. And so that gives me a category 2, basically for the same reason that monotone maps give me a category. Good? And now there are lots of other examples. Here, I'll give a fresh start here. Lots of other examples. Any kind of structured set together with homomorphisms of that structure, right? So things like groups, rings, if you're familiar with these algebraic structures. What about pointed sets? So we could have like sets with a point. That would be, the objects would be pairs consisting of a set together with a distinguished element, and the maps would be functions that take the distinguished element to the other distinguished element. There are lots of examples like that. Or posets with a bottom, and then the maps have to preserve the least element in the poset. Or posets with a, say, a join operation on the elements, and then the maps have to preserve the joins, and so on. So all kinds of examples of structured sets give rise to familiar categories. Of course, there are the more traditional ones, like the category of topological spaces, the category of differentiable manifolds and smooth maps, and on and on and on. So there are lots of examples of categories like that. Not to give you the impression that the arrows in a category are always supposed to be functions. That's a popular misconception coming from these kinds of examples. You could have, for example, the category of relations where the objects are sets, but the arrows are relations. So an arrow R from A to B is a relation, arbitrary, not functional, on A cross B. And then you have to come up with a clever way of defining composition of relations. And so that's an example that you see sometimes. If you look in, oh, I forgot to say, there are lecture notes on the web. There's also a whole PDF of a whole book. My book is on the web for you to use. Please don't put it on Wikipedia, okay? Just use it for this class, but don't circulate it. I've had to take it off from Wikipedia several times. So, and you can see these kinds of examples worked out. So there are lots of examples of categories where the arrows are not functions. See if there's anything else I wanted to be sure to mention. Oh yeah, here's another kind of example. This one is going to be a homework exercise. It's an example of a very different kind. It's a category of proofs. Category of proofs. Let's suppose we have some deductive system of logic. Logic could be propositional logic, let's say. And let me write and have some formulas. I don't have to be very specific about this. So I have some formulas. And then I have a notion of deduction of formulas. And I do need to have deductions. I do need to have deductions from premises, just to make things simple. So let's say I have a notion of a deduction like this. I go from here to here. And I want to consider this deduction. Let me call that P. So maybe it's this notion. But it's not just the notion of deducibility. It's deducibility by a particular given deduction that takes me from the assumption phi to the conclusion psi. Maybe it's a system of natural deduction, and the idea here is you've canceled all the premises but one, right? Or you can come up with other formulations there. You could have an axiomatic Hilbert-style system or whatever. Okay? So now you can guess what the objects and the arrows are going to be. These are the objects. These are the arrows in our category. Okay? How will we do composition? Well, let's suppose we have a deduction like this. So that's P. And then we have another one here. To be composable means these things line up. So here's a conclusion in this deduction. Here's an assumption in this deduction. We do the obvious thing now. We plug this in for this. The composition of these two things is going to be the deduction that starts from phi, goes down to psi, and then keeps on going and ends in theta. So that's the composition. Is that obvious deduction? The unit deduction is the trivial proof there that assumes phi and concludes phi at the same time. That's the unit. That's one phi. So is this a category? Looks pretty good, doesn't it? We've got the objects, we've got the arrows, we've got the domain and the codomain, we've got the composition, we've got the identity. So now we just have to check the laws, right? So how about the associativity? Is this operation going to be associative? Yeah, you can just look at it and see that it's associative, right? It's plugging things together. It's obviously associative. What about this? Does this satisfy the unit law? Yeah, it does. It's obviously a unit for that operation. So there's a nice category. And an interesting thing about this category, we could define a category like this too, by saying define the ordering on the formulas of deducibility, not deductions. That's obviously it's not quite a partial ordering. It's what's called a pre-order because it's missing the anti-symmetry condition, but it's basically a pre-order. Then it would be a pre-ordered or partially ordered category like that. There would be at most one arrow between any two objects. That wouldn't really be the category of proofs. That would be the category of provability, or the category of formulas, or something like that. This is a much more interesting category, right? This category has the whole proof theory of the system in it, because different proofs are different arrows. This thing is not a poset or pre-ordered category. you can have many different proofs between two formulas, and those are different arrows between those objects. Yeah? So this category can have a very interesting and rich structure, and in fact it does in general. Even in something as simple as a positive fragment of intuitionistic logic, intuitionistic propositional logic, just the positive fragment with conjunction and implication, that has a very rich proof theory. It's basically the simply typed lambda calculus. So in this category. So we'll get to that, I hope, in the next lecture. I'll be able to explain that. Okay, so that's enough enough for examples. Now what I'd like to do is look at some constructions that give us new categories out of old. There are, billions and billions of categories out there, and we can only get a glimpse of a couple. But even at that, once you get started, then you can make lots of new categories out of old categories. And that's what we're going to do next. So some constructions on categories. Let's look at some constructions. Oh, that's better. Even I can see that better. Constructions on categories. Let's try a product category. If I have a category C and another category D, I'm going to make a product of those two categories. So the objects are going to be pairs C, D, with C from C and D from D. And the arrows are going to be just pairs of arrows, let's say F, G, with F going from C to C prime and G going from D to D prime. And then I'll do the identity arrows. So the domains and codomains are the obvious ones that I've written down here. The identity arrow is just the identity in both components, right? So the identity on the pair C, D is just the pair 1C, 1D. And similarly, the composition of, let's say, F prime, G prime is just going to be component-wise. F, G is just F prime.